Hi everyone, so today we're going to be looking at 8.6, which is focusing on salts. There is a PowerPoint lesson to this lesson that you're more than welcome to take a look at. We're not going to review it today, we're just going to fill in this worksheet, but I do recommend that you do take a look at it just so you get a better understanding of it, so you have all the information as well as it's additional, so it's always a great idea to take a look at it. It has a great summary of the acids and bases properties of salt that I'm going to reference in the textbook as well. So I do recommend you take a look at it just as additional, and you can also go through some practice problems as well for practice. But today we're going to be looking at the lesson note. So focusing on this of salts, when we look at salts at room temperature, they're a solid and they're composed of cations and anions, and they're arranged in a crystal lattice. So when we look at salts, they do dissolve in water, and when they do, they dissociate into an aqueous solution where we have our ions that may or may not affect the pH overall. So when we look at the acidic or basic property of salt, we can look at its reaction that it reacts with water and the dissociation of ion in that salt. So salts can form neutral solutions, acidic solutions, and basic solutions, and we're going to be able to identify all of those today. When we have salts that form neutral solutions, the salts with the cation of a strong base or a salt of an anion with a strong acid, that is how we create a neutral solution. So we have the cation of a strong base or salts from an anion of a strong acid. So these are two examples here that we can see. The HA is a strong acid, and so therefore its conjugate base, which is the A, is so weak that it actually does not react with water. So because it's so strong of an acid, it doesn't react. And the same thing with the example below. If we have B and B is a strong base, its conjugate acid is HB, is going to be really weak, so it can't react with water, and therefore it is a neutral solution once it goes into water. So that's how neutral solutions work. Salts that form acidic solutions, so we have our salts where we can have our cation is a conjugate acid of a weak base and the anion of a strong acid. So that is one way that we can create acidic solutions. So we have our cation, which is positive, is the conjugate acid of a weak base, and the anion of a strong acid. We can also have non-metal oxides that can form acidic solutions, or we have salts where the cation is highly charged metal ion and the anion is a strong acid. So we're going to look at some examples here. So we have the original equation to form the ion. So our NH3 is seen as a weak base. Then we have our acid. It creates our NH4, which is our conjugate acid, and then we have our conjugate base. So once we have this reaction that goes together, it does create our ions in the water. And if we look at our chart on page 501, we can see that NH4 is much stronger than water. So that means the pH is going to be greater than 7. Less than 7, and this is known as hydrolysis. So because NH4 is acidic, it is actually stronger than water, and so it creates a solution of a pH that is actually going to be less than 7. So that is how an acidic solution can form. We can look at the pH. We can also look at basic solutions where we either have metal oxides that are reacting, or we have salts with the cation of a strong base and an ion of a weak acid that form. So once again, taking a look at the chart on page 501, we have our weak acid, we have our base, then we create our conjugate base, and then our conjugate acid. In this situation here, if we look at the on page 501, we can see CH3CO ion is stronger than water, and It's opposite of our acidic solutions because we're looking at basic. So because of that, it is greater than 7, and that means we know that it is basic. So whenever we look at salts of a weak acid and base, we can look at the pH of a salt. So this is one point that we can take a look at to determine if it is acidic, basic, or neutral. So if the pH of the salt, the cation is the conjugate acid of a weak base, and then the anion is the conjugate base of a weak acid. This will help depend if the conjugate acid value is going to be Ka and the Kb value of the conjugate base. So I would recommend taking a look at page 537 for other rules, because that's going to be really important to note. But if the Ka is greater than Kb, then it's going to be acidic. If it's opposite, it's going to be basic. If they're equal, they're going to be neutral. And we're going to look at some examples now to look at how to predict the behavior of salt. So we're going to have different examples here. So we have Na3PO4. So in this situation here, Na is a metal and it's in group 1. So that means there's no reaction that's going to occur. There's no reaction that is going to occur at all. So because of that, it's not going to react with water, but we do have PO4-3, and this is actually a weak acid and it's going to react with water. So we can see the reaction here. We have PO4-3 and H2O react to produce HPO4-2 and OH. And because it creates this OH, we know OH is a strong base, so it's going to be basic. Now looking at some other examples, we have NH4NO3. In this situation here, we have NH4. We know NH4 undergoes the reaction, and this always reacts with water, and it creates NH3 and H3O. So because of this, we see the H3O, it is therefore acidic. But we know NH4 is a conjugate acid of the weak base NH3, and so therefore it reacts with water. And we can look at that page and that table on page 501 to determine that. Now we have NaCl. Na and Cl, because they are both in group 1 and 2, they do not create any reaction with water, so therefore it is neutral. That means pH is going to be equal to 7. And then our last example here, this is really unique, this one. So we have NH4, which we just talked about in B, but HCO3 also is going to react with water. So when we look at NH4, this is a conjugate acid of NH3, and then HCO3 is a conjugate base of our H2CO3. So therefore, since they're both are coming up with weak components for our conjugates, they are going to both react with water. So we're going to look at these reactions here. So we have NH4 reacts with water. We just saw that in example B. And when we look at the Ka value, we can look at that in our textbook. Please reference the tables in our textbook. They are at the very back of our textbook. And all the Ka, Kb values are given there. So the Ka value is, actually, this is, yeah, that's fine. It's going to be seen here. When we look at Kb for NH3, it's 1.8 times 10 to the power negative 5. We are going to use the equation Ka-Kb equals Kw, which we've seen in the past. As well as we can look at HCO3, it reacts and creates, we see our Kb value, and we're going to use Ka equation to solve for HCO in order to calculate it. So NH4 reaction is figured out, but HCO3 we need to solve for Ka. But in general, since both of them are forming some sort of reaction, and since our Kb, if we look back on the previous page, since Kb is greater than Ka, when we look at our H3O and our OH, once we solve for this, we will know that our Kb is greater than our Ka. Both these values are greater than our Ka value. Once again, we're going to solve for this one in a moment, but it will be. We know that the solution is going to be basic. And now we're going to prove that. So we're going to prove it here. So for a 0.10 mole per liter solution of NaNO3, when we're looking at something like this, we can predict the solutions of, oops, sorry, there was a little typo up here. Let's go back a little bit, sorry. This was a little typo. I just want to make these corrections so we are correct. And we know. There we go. So right now we're going to look at how we can look at the steps for pH of salt. So we have 0.10 moles per liter solution. We're going to predict if it's acidic, basic, or neutral and calculate the pH. So this is another example to determine how it's basic. And once again, very similar to this point up here of how we can determine and find our Ka. This is how we would do it. So when we look at this information, we have NO2 and H2O. If we were to look at this information, our OH is a very strong base, and we have a weak acid, so therefore it's going to be basic. But how do we prove this? We are going to we're going to predict it, but we're now going to calculate to prove it. So using this information, this actual calculation is to be 4.6. We're going to plug in our Kw divided by our Ka, and we will get an answer of 2.2 times 10 to the power negative 11. Now putting this information into our ice chart, we can solve for our K, which is going to be 2x over 0.10 minus x. Because our information, we're going to use our approximation method. So using our approximation method, if we were going to take our 4.6 times 10 to the power negative 4 divided by 2.2 times 10 to the power negative 11, it would get 20 million. So therefore, because we know it's way greater than 500, we can get rid of this x value, and now we can solve for x. So we're going to take this 2.2 times 10 to the power negative 11, which is going to be equal to x squared over 0.10. We're going to multiply, and we will get x equals 1.48 times 10 to the negative 6. Now, in order to solve for our OH, we will obviously know our OH is what we just found because it's x. Now we can solve for POH, which is going to be our negative log of this value. So we're going to plug that value in, and we'll get 5.83, and then 14 minus 5.83 will give us 8.17, so therefore it is basic. So given this information, try this out, use the practice questions here, calculate, and then work on the homework, okay? If you have any questions, please let me know. Try to calculate these examples